Welcome to today's Explainer. Today, we are opening up the ultimate geographer's toolkit to decode exactly how we map, measure, and truly understand the world around us. We aren't just looking at flat, boring maps here. We're going to break down the hidden structures, the wild imagery, and the hard data that let us make sense of our incredibly complex planet.
Here is our roadmap for today. 1. The Earth's invisible grid and exact location. 2. Understanding global time zones. 3. Interpreting geographical photographs. And 4. Reading climate data graphs.
But before we get into the data, I want you to picture this. Imagine you're the captain of a ship, and you've just encountered some serious trouble out in the middle of the ocean. You desperately need help, so you radio the Coast Guard. The very first question they are going to ask you is, where are you? Now, you can't exactly say you're near the big wave or just past those seagulls, right? You need an exact, universal language to pinpoint your location in a vast, featureless ocean. So how exactly do you do it?
Section 1. The Earth's invisible grid and exact location.
That life or death scenario is exactly why humanity had to develop our first set of geographical tools. To find absolutely any spot on Earth, we first have to slice the globe into measurable pieces. We start with latitudes, which are also known as parallels. These are imaginary lines drawn perfectly parallel to the equator. They encircle the Earth entirely in an east-west direction. The equator is our starting point. It's the widest latitude and is marked as exactly 0 degrees. It splits the whole planet right down the middle into the northern hemisphere and the southern hemisphere.
Notice how these lines wrap around the globe. As you move away from that 0-degree equator, whether you're going north or south, the value of the latitudes increases. They keep going up and up until they hit a maximum of 90 degrees north right at the North Pole and 90 degrees south at the South Pole.
But here's the thing. Horizontal slices just aren't enough to pinpoint a specific spot. We need vertical slices too. These are called longitudes or meridians. These are imaginary lines that run in a north-south direction. But unlike latitudes, they do not run parallel. Instead, they run from the North Pole straight down to the South Pole. Their starting line, their 0-degree mark, is a line known as the prime meridian, which famously passes right through Greenwich in London.
Take a look at how all the lines of longitude converge or pinch together at the very top and bottom of the Earth. Just like the equator, the prime meridian divides the Earth, but this time into the eastern and western hemispheres. If you move east from the prime meridian, you count up to 180 degrees east. Move west, you count up to 180 degrees west. And right at the back of the globe, at exactly 180 degrees, those two sides meet at a crucial marker called the international dateline.
So the crucial point is knowing how to never get them mixed up. It's actually pretty simple. Latitudes are parallel. They run east-west, like the rungs on a ladder, starting at the equator. Longitudes are converging. They run north-south, like the segments of an orange, starting at the prime meridian.
Okay, so back to our stranded ship captain. How do they actually use this invisible grid? It all comes down to 3 steps. Step 1, you identify the latitude line for your location, noting if it's north or south of the equator. Step 2, you find your longitude line, noting if it's east or west of the prime meridian. And step 3, you simply locate the exact point where those 2 specific lines cross on the map. That intersection is your unique, totally unarguable location on the globe.
Let's see it in action. If our ship's captain calculates their latitude at 50 degrees north and their longitude at 30 degrees east, the rescue crew simply follows the 50 north line horizontally and the 30 east line vertically. The exact spot where they cross is exactly where that ship is floating. This brilliantly simple system has literally guided sailors, pilots, and geographers for a very long time.
Section 2. Understanding global time zones.
Now that we have our grid locked in, we run into another fascinating geographical challenge: time. The entire key to coordinating global time lies in one magic number, and that number is 15. Because our Earth takes 24 hours to complete a full 360-degree rotation, we can divide 360 by 24, which gives us exactly 15. This means that for every 15 degrees of longitude we move eastwards, local time jumps ahead by exactly 1 hour. If we move westwards, it falls behind by 1 hour.
Now, back in the 19th century, this wasn't really an issue, until widespread railroad travel made everyone's local town clocks totally confusing. Imagine trying to catch a train when every town has a slightly different time. So, a Canadian engineer named Sir Sansford Fleming proposed a brilliant system of universal standard time based on those 15-degree segments. Here's how it works today. Step 1, you start with the Worldwide Standard Time, or UTC, at the prime meridian. Step 2, you add hours for locations to the east. And Step 3, you subtract hours for locations to the west.
When we lay this system out across a map of the globe, it is incredibly elegant. You can easily spot the prime meridian running right down the middle at 0. Look at the numbers along the top there. If you travel east to a pink zone, let's say +3, you literally just add 3 hours to the UTC time. If you travel west to a yellow zone, like -8 over in California, you subtract 8 hours. It's a beautifully structured system that keeps the whole world ticking together.
Section 3. Interpreting geographical photographs. Invisible grids and time zones are absolutely essential, but geographers also need to physically see the real world. I mean, you don't have to visit the Great Wall of China to know what it looks like, and we have photography to thank for that. In geography, we mainly rely on 3 distinct types of photographs to analyze features. We have landscape photographs, which are taken right down at ground level. We have aerial photographs, usually captured from airplanes. And finally, we have satellite images, beamed all the way down from automated spacecraft orbiting hundreds of kilometers above the Earth.
And when it comes to capturing these, the camera angle changes absolutely everything. On the left here, we see a vertical aerial photograph, which means the camera is pointed directly straight down at the ground. It looks almost exactly like a map, making spatial patterns highly visible. On the right, we have an oblique aerial photograph. Here, the picture is taken at a slant, or an angle. It gives you a much better sense of the height and 3D shape of buildings, like here in downtown Tokyo, but it covers a bit less area than a vertical shot.
But when we zoom way out to satellite images, things get really wild. Satellites often record infrared energy from the Earth's surface, energy that human eyes literally cannot see. When that data comes back to Earth, computers assign quote-unquote false colors to it so we can actually interpret it. This table right here, this is your ultimate decoder ring. If you see white or cream, you're looking at a beach or sandy area. But get this, pink or red actually means vegetation and trees. Deep red or magenta, that means dense forest. And dark blue or black represents deep waters.
Without that decoder ring, a satellite image can just look like a bunch of strange red shapes. But now we know that all that bright red and pink represents farmland and heavy vegetation. And those black grid-like lines in the foreground, those show where a river system is cutting right through to provide water to those farms. Having this tool completely changes how you can analyze a region's natural resources from space.
Section 4. Reading climate data graphs.
Okay, we've plotted coordinates and decoded infrared space photography. Now we move to hard data visualization. Imagine looking at a giant spreadsheet listing every single drop of rain and every degree of temperature over a whole year. It would be completely overwhelming. That's why we use graphs to get an instant picture of the variation over time. The 2 main types geographers use are bar graphs and line graphs. A bar graph uses side-by-side vertical bars, which is perfect for comparing amounts, like exactly how much it rained in a specific month. A line graph, however, uses a plotted line connecting data points. This is ideal for showing continuous changes over a period, like how temperature gradually rises and falls.
Take this rainfall data for Dodoma, Tanzania, for example. The x-axis across the bottom shows the months of the year, and the y-axis shows the amount of rainfall in millimeters. You don't even need to look at the exact numbers to see the story this data is telling us. Those massive blue bars show us immediately that from December to March, there is a severe wet season. But from May to October, the bars disappear almost entirely, instantly revealing a very intense dry season.
Now let's contrast that with a line graph. This one plots the temperature for Berlin, Germany. Again, months are on the x-axis, but here the y-axis is temperature in Celsius. Because temperature changes in a continuous flow, the line connects the data perfectly. You can clearly trace how the temperature pattern starts cold, right around 0 degrees in January, rises steadily to a summer peak of 19 degrees in July, and then falls right back down as winter approaches. It gives us a flawless visual rhythm of Berlin's climate.
Well, we have covered a massive amount of ground today. You've mastered how intersecting latitudes and longitudes pinpoint exact locations. You've learned how the Earth's rotation dictates the addition and subtraction of hours across standard time zones. You've unlocked the hidden data inside false color satellite imagery. And you've learned to read the stories hiding inside climate graphs. So I'll leave you with this question. Now that you possess this incredibly powerful geographer's toolkit, how will you use it to reshape the way you understand and navigate our amazing world? Keep exploring, and I'll catch you on the next explainer.